What it means is that regular languages are closed under the regular operations. Regular languages are closed under regular operations. What do we mean by this? What do we mean by this statement? Regular languages are closed under regular operations. Closure. Are you familiar with the concept of closure? So what does closure mean here in the context of regular languages? So regular operations, what are regular operations? Regular operations are union, concatenation, star. So what does it mean when we say regular operations are closed under union? It means that if you take the union of two regular languages, you get a regular language. When you take the union of two regular languages, you get a regular language. When you take the concatenation of two regular languages, you get a regular language. When you take the star of a regular language, you get a regular language. Now, how did we define a regular language last time? What's the definition of a regular language? A regular language is a language that can be recognized by a DFA. Yeah, it can be recognized by a DFA. And we can also say that it's a language that can be recognized by an NFA, because we proved that DFA and NFA recognize the exact same set of languages, even though NFAs can give you more options and can recognize the same language in a more compact way with fewer states than a DFA, but they still recognize the same set of languages, which is regular languages. And in fact, regular expressions also generate the same set of languages, which is something that we will prove later. So we will see at the end that DFAs, NFAs, and regular expressions, all of them recognize or generate the same set of languages, which is the set of regular languages. Now, so in order to show that regular languages are closed under union, what we need to do is to show how we can always, if you have an NFA or a DFA for a language, for language 1, and an NFA for language 2, you can always construct an NFA for the union of the two languages. Okay, so now we'll do the concrete, then we'll do the abstract. So the concrete is an example. So let language 1 be W such that W contains the substring 1, 0. And L2 is the language W such that W ends with 1. Of course, my segment here is 0, 1. Okay, so an NFA for L1. Now it should be easy. NFA for L1 containing a substring, very easy. This is the 0, 1. And then what should I do?
First one accepts anything.
Yeah, you can loop on anything. So this is the anything, or the sigma star. And this is the anything. And this is what? Accept state. So this is a string for the language that contains a certain substring, which is in this case 0, 1. NFA for L2. The NFA for L2 is going to be ends with 1. So I have to have 1 at the end. And then what?
Anything before that?
Anything before that, yeah. So there is a loop before. Anything that ends with 1. Yes?
For the NFA for L1, are we looking for the substring 1, 0, not 0, 1? That's what you have in the definite.
Oh, I keep making mistakes today. I don't know why. Yeah, I don't know what's happening today. Yeah, you're right. It's good that you guys are alert. Yeah, I'm making mistakes today. Yeah, so it's definitely 1-0. Same substance. Okay. Okay. So now how do we construct an NFA for the union? The NFA for the union can be constructed in a straightforward manner by branching using epsilon transition. So you have an epsilon, then you put the NFA for the first language and then the NFA for the other language. Because you have two options. That's a straightforward way of representing the union, because the union says that a string can belong, if a string belongs to this or this, it will get accepted. So union is or. And or is just, we just put two paths or two options. And that's why NFAs are much easier to work with than DFAs. So you just do this and then you put the NFA for 1, 0. 0, 1 and 0, 1. Oh, I don't have much space on this board. And I have 1 and I have 0, 1. So you just, this is option number 1, language 1. This is option number 2, language 2. Okay. Now, let's generalize it, but in graphical form first. So given two languages, you have NFA for L1, which looks like this. So now I'm going to try to draw a general NFA. It will have a start state, and it will have a bunch of internal states, and it will have some accept states. So this is an NFA for L1, and this is an NFA for L2. I'm going to draw it differently just to distinguish between the two. So I'm going to give it 3 accept states. And I'm going to put something, okay, it has a start state. And I'm going to put something like this, internal state. So just trying to draw two different languages, general languages. So any language, any NFA will have one start state, and it can have an arbitrary number of accept states, and in the middle it can have an arbitrary number of other states that are neither start nor final. Okay, now in general, an NFA for the union, NFA for L1 union L2 is going to look like this. So I'm going to, so this state, I'm going to add one new state. Then I'm going to branch on epsilon. I think I need more space. Yeah, limited whiteboard space in this room. And then I will have the first NFA, and then so this is NFA1. NFA1 is going to have this, and NFA2 is going to be this. So now I'm doing it in general to show you that given any two regular languages with an NFA recognizing each one of them, so you have an NFA for L1, NFA for L2, no matter what these NFAs are, in general, you will always be able to construct an NFA for the union by doing this, by branching. Epsilon, and then this is the NFA for the first language, then this is the NFA for the second language. Okay, yes?
You could join infinite amount of NFAs, right? You just have a whole bunch of epsilons to a whole bunch of other.
Oh, if you have more than 2 NFAs, yes, you can certainly do that. If you have more than 2 NFAs, you can do that. But for now, we are just showing it for 2 NFAs, and you can easily generalize, because once you construct an NFA for the union of L1 and L2, you can union that with L3, and then you can union that with L4 and so forth. So you can repeat this as many times as you want. All right, so now, I would like to write the formal description of this language. So let me see if we can fit this. Given an NFA 1 equals Q1 sigma delta 1 and Q1 and F1 for L1, and an NFA 2, which is equal to Q2 sigma delta 2 Q2 F2 for L2. What I'm trying to do now is to, generalize this using the formal description of NFAs. So this is generalization, graphical generalization. Now I'm turning this into an algebraic generalization using the formal descriptions of NFAs. So in general, you will be given 2 NFAs. Each one has Q1, which is the set of states. Sigma is the alphabet. We assume that it's the same alphabet, but the procedure is going to work even if you have different alphabets. Delta 1 is what do we call delta? Transition function for the first one. Q1 is start state, and F, set of final states. We can construct n NFA for, let's call it NFA n, equals Q sigma delta Q sub S and F for the union of the 2 languages. So for L1 union L2 as follows. Okay, so in fact I will have to erase this so that I can use the space here. Okay, so what will be the relation between Q for the union and Q and the Q1 and Q2 for the original language? What will be the relation? What's the relation between Q and Q1 and Q2? So here's Q1, here's Q2. What's the relation between Q?
It's Q1 union Q2?
Okay, exactly. So it's Q1 union Q2, and look at this. Is it only Q1 union Q2?
No, there's another Q.
You missed this.
Yeah.
So this does not belong to either U1 or so union, another state that we have added. So this is our QS. Union QS as a set. where QS is a new start state that we add. Okay, QS is a new start state that we add. This is the relation between Q1, Q2. Sigma is sigma. Let's leave delta to the end because delta is the most interesting part. Now, what's the relation between QS and Q1 and Q2? Well, in fact, there is no relation. QS is just a new state, a new start state that we add. So we don't have to say anything. We just said that QS is a new start state that we add, and it has nothing to do with Q1 and Q2. Now, what's the relation between F and F1 and F2? So this is F1, this is F2. What's the relation between F for the union?
F1 union F2.
Yeah, exactly. It's F1 union F2. Now delta is the trickiest part. Delta of Q and X equals, now delta of Q and X, if delta for the states that belong to this, to Q1, then delta is not going to change. For the states that belong to the second NFA, their transitions are not going to change. We only have to define the deltas for the new state that we have added. So it's going to be delta 1 of Q and X if Q belongs to Q1, and it's going to be delta 2 of Q and X if Q belongs to Q2. So if it's an original, one of the original states, its transitions are not going to change because we did not touch them. We didn't touch them. We just merged them. We combined them. We connected them with these epsilons. We did not add any new transitions. Okay? And now we have to define for QS. If Q equals QS, Q sub S, then what should the transition be? What are the transitions for QS? If X equals epsilon, what are the transitions? Where do we go? So what's this? So this is Q1, and this is Q2. So if Q equals QS and X equals epsilon, then I have the set Q1, Q2. So QS transition on epsilon, I go to the set Q1, Q2. Now what if it's not epsilon? What if Q equals QS and X is not equal to epsilon? Where do I go? There is no transition. What does that mean? Empty set. Yeah, you go to the empty set of states. This is an NFA, not a DFA. So the trap is implicit. So you go to an infinite. You go to an empty set. So this is the formal description of the union. So transitions basically for original states stay the same, but you have to define the transitions for the new state that you have added, which is QS, and there are two kinds of transitions for this. A transition if the symbol is epsilon, and the transition if the symbol is not epsilon. Okay? Now I'm going to do so this proves that you can always construct an NFA for the union. Now what about the concatenation? So I'm going to put, I have to keep erasing because I need to use the space. So it's like running a program with a small cache. I keep, yeah. So I don't need this anymore. So again, this is L1. I'm going to go back to the, was it 0, 1 or 1, 0?
1, 0.
1, 0. Okay, 0, 1, 0, and okay, so how do we construct an NFA for the concatenation?
You add it to the pen.
Yeah, you stick them together. As simple as that. But we'll see that mathematically there will be some subtleties in expressing this sticking mathematically. So in English we just stick them together, but stick them with what? What do we use to link them together, you think? Epsilon. We use an epsilon to link them together. So you link them using an epsilon, an epsilon link to link them. This is wrong. I will ask you what's wrong after I'm done. So try to figure out what's wrong with what's on the board now. And then the other language ends with 1. So this is an NFA for the concatenation, but it has one error. What's the error in this language for the concatenation of the two languages that I had? Where is the error?
Be able to exit out of the final state whenever you want via epsilon transition.
Here?
No, it's the middle one, the first. Yeah, you can epsilon transition right out of that if you really want.
That's okay. The epsilon is not an error. Where is the error? I'm trying to express the concatenation. Concatenation, what does concatenation mean? It means that every string that belongs to this language has to have two pieces, a prefix and a suffix. The prefix belongs to language 1, the suffix belongs to language 2. So in order for the string to qualify for this language, it has to have two pieces.
So there shouldn't be an accept state before.
Exactly, yeah, exactly. That's the answer. This should not be an accept state, because if we leave it as an accept state, we will be accepting only the prefix. No, in order to belong to the concatenation, you have to have two pieces. One that belongs to language 1, one that belongs to language 2, and this should no longer be an accept state. Okay? Now, let's do it in general. So let's do the sticking or the linking graphically. So I'm going to do this. So this is the NFA for language 1, and I'm going to connect it. Now, I can't connect the box. I should connect states. So I'm going to connect these states. And this is okay. Again, fix the error. What's the error? Yeah.
Oh, there was a question about something on the previous one.
Yes.
So do you still need the looping on the previous accept state for 0 and 1 before the epsilon transition? Because you can just go anywhere after that, right?
So
Do you still, would it be redundant to have that looping right there? So after the 1, 0, you have the loop of 0, 1. Is that still necessary?
yeah, it's still necessary. You don't touch. You don't change anything in them. So how can you accept a string whose prefix has 100, 100 symbols in it with 1, 0? So like 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. Oh, sorry, this ends with 1. So for this example, it's not a good example. What about this? How will you accept this? So you need this in order to accept this. So this is the 1, 0, and then you can have as many
Okay.
as you want. Then you can have something that ends with 1.
Just get simplified.
Okay? So now, what's the error here?
The acceptance.
Yeah, so these are no longer accept states. Okay? And now this is Q1, this is Q2, and this belongs to F1. So this set is, this is F1, this is F2. Okay, now we can construct an NFA for L1 concatenation L2 as follows. Okay, now I have to erase this. Now let's figure out the formal description of the language that's the language that the NFA that represents the concatenation. Okay, now what's Q? What's Q in this case? So this is Q. How does it relate to Q, to the original Q1 and Q2?
The union.
It's the union. We don't have an additional state here. We did not add any new states. So Q is Q1, Q1 union Q2. If I think, did I have this Q originally? So this should be Q1 union Q2. So this is, if I had it wrong, fix it. This is Q1 union Q2. Was it Q1 union Q2? Yeah, so this is Q1 union Q2. Okay, so now, what's QS? What's QS for the concatenation?
There isn't one.
It's what?
There is one.
Q1.
Every NFA has a start state. What's the start state of the, look at the concatenation. Where is the start state here?
Q1.
Yeah, it's Q1. So QS is equal to Q1. Now what's F? Where is F for this concatenation?
That's
F2.
F2.
It's F2, yeah. F is F2. Okay, now delta, that's the interesting part. Now delta of Q and X equals delta of Q and X. I'm trying to survive with little space. Q and X equals. What's delta for the original states? Did I change the transitions for the original states in Q1, in the NFA1?
No.
Yes, I did. I changed it for which states?
Fine.
For the final states. So if it's any state, in fact, the final states in F1 are the only states that I have, for which I have changed the transitions. Everything else, I did not change the transition. So if it's going to be equal to delta 1 of Q and X, if Q is what? If Q does not belong to F1. Any state that does not belong to F1, it stays delta 1. The transitions stay the same. But what if Q belongs to F1? If Q belongs to F1, now it depends on whether X is epsilon or not. So if Q belongs to F1 and X equals epsilon, I have something. And if Q belongs to F1 and X, well, let's do the not epsilon here. And then X equals epsilon. Now what if Q belongs to F1 and the transition is not epsilon? Did I change it? In fact, I didn't, because this could have had transitions on A and B. I did not touch them. I added the epsilon transition, but I still kept the ones that were originally there. So if X is not equal to epsilon, everything stays the same, delta 1 of Q and X. Now for the epsilon transition, again I could have had an original epsilon there. I could have had an original epsilon. So I added another epsilon even though I may have had an original epsilon there. So what would be the transition for Q if X equals epsilon in this case? Given that I may have had original transitions for epsilon, I'm adding additional transitions for epsilon for these states. So what should I write here? How would I express this mathematically? I'm keeping everything that was there, and I'm adding a transition to Q2. So this is going to go to delta 1 of Q and X union Q2. So I'm adding the set Q2 to the set of transitions for these final states. Okay, now what if Q belongs to what if Q belongs to F2? Okay, look at this. Did I change any transition here? The only place where I changed transitions is for those that belong to F1. Here I didn't touch anything. Okay, so this is going to be delta 2 of Q and X. Okay. All right. So this is the mathematical abstraction. This is the graphical form. This is the mathematical abstraction. Okay. Any questions? So just think about the states. What transitions are we changing? What transitions are we adding? Yes?
Is that F2, should that be a Q2? The delta, the transition table, right? The transition function, should that be if Q
Yes,
is
yes,
Q2?
yes, you are right. Yes, that's Q2. If Q does not belong, in fact, this should be Q belongs to Q1 and does not belong to F1. So this should be Q belongs to Q1 and Q does not belong to F1. And this is Q belongs to Q1 and Q belongs to F1. And this is Q belongs to Q1 and Q belongs to F1 and X equals epsilon. Yes. So here when those are for the states that belong to Q1 and those are for the states that belong to Q2.